Hi everybody, I am Rama Koteshwara Kotamasu. This is my CS682 term project demo for Twin Pharma OS. This is the term project. This project started in part 1 as a requirements exercise, and over 4 assignments, it grew into a fully working application. So in this video, I'm going to quickly walk through what I designed, show you some of the key diagrams, and then open the actual app I built and show you how the design translates into working code. So let's start at the beginning. So Twin Pharma OS is a remote clinical trial management platform. The core problem it solves is this. In remote drug trials, patients wear IoT sensors at home. When those sensors fall off, which happens a lot, the whole data record can be invalidated under FDA audit rules that kills the years of pharmaceutical work. My system fixes that by using a generative AI engine to automatically fill the data gap whenever a sensor drops out, and then gives the statistician, sorry, a structured workflow to audit, verify, and log those synthetic data blocks into a regulatory ledger. So I have two user stories, one for biostatistician who reviews the data, and one for the patient at home who just wants a simple alert to reseat their sensor. Both drove every design decision that came after. Okay. So I specified about 14 functional requirements across 4 modules: the IoT data ingestion, generative AI simulation, the admin dashboard and audit workflow, and the patient mobile interface. The two I want to highlight are functional requirement 4.1.2. 1.2, the chest patch dropout fires when adhesion voltage drops below 0.5 volts. And another one is 4.2.2. The synthetic data must stay within 2 standard deviations of the patient's baseline. These two requirements show up in every design artifact after this. Okay, so state machine diagram, let's go to that. Okay. So the state machine has 5 states. The system starts streaming live telemetry, detects a dropout, goes into a synthesizing phase, which has 4 substates of its own, renders the synthetic overlay, and finally finalizes a data block into the regulatory ledger. That finalization is terminal. Once it's done, it cannot be undone. Okay. So let's go to the class diagram. Second. Yes. So Okay, in part 2, I have created built the class model. So this class model, okay, so this is the class model. So this class model has 13 classes organized across 3 packages. Um, Across 3 packages. Okay, so let me. Yeah. Okay, so this is the class diagram. So it has 13 classes organized across 3 packages. The participant monitoring package handles everything about the patient, the biometric timeline, the IoT device readings, the synthetic data blocks. The synthetic audit package handles audit lifecycle, audit ledger, compliance ledger API, and synthetic data block live here. The key design decision made is that 2 packages only communicate in one direction. The audit package knows about synthetic blocks, but the monitoring package has no idea auditing even exists. That keeps them independently reusable. Okay, so let's go to the sequence diagram. Okay. The sequence diagram covers use case 5.1, the full audit workflow. The thing I want to point out is step 4. It's a little bit smaller here, but audit ledger calls lock block on synthetic data block. That lock call belongs on the ledger, not on the controller, because the block should only become read-only at the moment the audit entry is actually committed. So we caught that during modeling. Okay, so let's move to the activity diagram and pseudocode. So this is the activity diagram. I picked commit audit entry method as my focus because it touches every package and has a meaningful decision branch. The activity diagram has 6 numbered steps. Given nodes are cross class calls. Yellow are internal operations. Red path is the alternate. Green are cross class calls. When the guard check fails and a block not ready exception is thrown, the ledger is untouched on that path. Okay, so let's go to the pseudocode. The pseudocode maps directly to those 6 steps. Step 6 was actually wrong in the first draft. I forgot to include the timestamp in the audit confirmation return, and the after the feedback, I fixed it by cross-checking the class model against the pseudocode side by side. This kind of consistency is exactly what a detailed design is supposed to catch. Okay, let me open the actual application now. Okay. This is the full application, 4 tabs: trial dashboard, audit ledger, medical monitor, patient view, fully working, all working. The system state bar at the top shows I'm currently processing stream interruption, which is a state 2 from the part 1 state machine. The Amber Alert banner confirms participant 4421 has a sensor dropout at 14 hours 23 minutes. The left sidebar has 6 cohort participants. 4421 has a green background because it's in the active view. And the amber dot on 4415 means it also has a dropout in progress. The gray dot on 4398 means that only one is already finalized. Okay. So now this is the window. So the chart shows 72 hours of rolling biometric data. Heart rate is in blue, and SPOT is in green, and amber dashed box is the AI okay, and skin temperature is the red. Okay, amber dashed box. So this is the box is the AI synthetic overlay window from 1423 to 1510. That's the gap the generative engine filled it. I can filter to AI only to see just the synthetic segment or see the physical only and all data as needed. So you'll notice it's a bit smoother than the physical signal. Thus, the two standard deviation constraint from FR4 to 2, which is working. Okay. So the right panel is the synthetic block detail, confidence score of 94.8%, variance per channel, all under 2 standard deviations. This is the use case 5.1 step 3. Okay, while clicking the verify synthetic, I'm triggering verify synthetic block integrity workflow. Normally initializes synthesis pipeline, validates block level consistency checks before moving into the audit phase. In the intended flow, this would cycle through 4 internal synthesis stages: initialization, generation, validation, and injection, each representing a controlled checkpoint in the processing pipeline. Here I am demonstrating the guardrail condition. If a block is already locked or not eligible for re-audit, the system prevents reprocessing through a block not ready exception. This ensures immutability of finalized audit states. This final step commits the audit entry. This final step commits the audit entry into the regulatory ledger. In the full implementation, this executes a 6-step commit process, ensuring traceability, timestamp integrity, and audit immutability. Now I will click verify block synthetic integrity. So currently it is a block not ready exception, which ensures the immutability of finalized audit states. Okay, let's go to the audit ledger tab. The audit ledger tab shows append only store, the part 4 addition to the class model. Every entry has a SHA-256 hash linking to the previous entry. The chain is NFR2 8.2. Cryptographically signed, append only, no deletion. I can click verify chain integrity to confirm every link is intact. Okay, let's go to the patient view tab. Quick look at the patient view. This is the use case 5.2. The chest patch adhesion voltage is live. I will simulate a dropout. Voltage drops below 0.5 volts. Voltage drops below 0. To the 0.1 volts. The reseating guide appears, and when I reseat it, it reconnects. Thus, FR 4.1.2 and 4.1.4 in action. The thing I will only take away from this project is how much easier the code was to write. The pseudocode, once the design was specific enough, the 6 pseudocode steps became 6 commented lines in the JavaScript method. The class package boundaries became the code module structure. The state names from part 1 are literally the same strings in the code constants. Wherever the design was vague, the code got messy. Wherever the design was precise, the code just followed. What I would do differently, I would add the can be finalized guard to the class model earlier in part 2 instead of part 3. Discovering it during sequence modeling delayed 2 artifacts. Better to get it right in the class model from the start. That's the Twin Pharma OS. Thank you for checking on this. I loved learning this course. Thank you, Professor.